Hello and welcome to another Grandstream tutorial. In this video, we're going to talk about the wireless standard 802.11ax, which is commonly referred to as Wi-Fi 6. Wi-Fi 6 has introduced several technical improvements to enhance throughput and spectral efficiency. In this video, I will highlight the key features implemented by Wi-Fi 6 and explain how they work to improve the performance of a wireless network. Before we get into that, I want to briefly introduce the Grandstream access point that supports Wi-Fi 6. First, there's GWN 7660 that comes with two antennas. It provides wireless throughput of up to 1.77 gigabits per second and a wireless connection to up to 256 concurrent clients. For high-density environments, we have GWN 7664 with 4 antennas and a wireless throughput of 3.55 gigabits per second. It can serve up to 512 wireless clients. Next is the outdoor access point, GWN 7660LR, equipped with 2 antennas, and it provides a wireless throughput of 1.77 gigabit per second. All Grandstream Wi-Fi 6 capable access points are Wi-Fi 6 certified, and there are new models that will be released soon, including GWN 7664LR with 4 antennas. So when comparing Wi-Fi 6 to earlier standards such as 802.11ac, the first big change is that Wi-Fi 6 allows for faster speed and a more reliable connection. It achieves this by using the wireless medium more efficiently, which allows it to handle the challenges of high-density environments better than earlier standards. So when using Wi-Fi 6, an access point with 8 spatial streams can provide theoretical maximum speed of 9.6 gigabits per second when using a channel width of 160 megahertz. Always keep in mind that Wi-Fi speed can be affected by multiple factors such as the signal strength, the channel width, and the number of antennas used by the access point. So while earlier standards were primarily focused on increasing wireless throughput, Wi-Fi 6 focus is to make the use of the wireless medium more efficient so that we can achieve the maximum throughput capacity. Now let's explain the major improvements in Wi-Fi 6. And we're going to start with the MIMO technology, which allows the access point to communicate with wireless devices using multiple streams. 802.11n was the first standard to introduce MIMO technology. And it uses single-user MIMO technology, which allows the access point to focus its spatial streams on a single user to increase data rate. However, this requires that the wireless client have multiple antennas as well. 802.11ac Wave 2 version improved the MIMO technology by allowing the access point to communicate with multiple wireless clients simultaneously instead of just focusing on a single user. And this is referred to as multi-user MIMO. And in 802.11ac, this works only for downlink. Wi-Fi 6 improved this technology so it can be used for both uplink and downlink. By leveraging multi-user MIMO for uplink, multiple wireless clients can now transmit data to the access point simultaneously. For example, GWN 7664LR, which has 4 antennas, can talk and listen to 4 wireless clients simultaneously by dedicating 1 stream or antenna per user. To meet the challenges of high-density wireless environments, Wi-Fi 6 introduced OFDMA, which is designed to maximize the transmission efficiency by allowing the AP to communicate with multiple devices simultaneously. Before we explain how OFDMA works, let's first look at how OFDM works on Wi-Fi 5 and earlier versions. The OFDM modulation in 802.11ac, for example, can only transmit data to a single user. It takes the whole channel to transmit to one user at a time. The problem with that is that there is usually wasted spectrum that is not used during a transmission, especially when transmitting a small data frame. For example, T4 in this image shows how a whole channel is used to carry a small data frame, which leads to a big part of the channel not being used. So OFDM is not efficient in how it uses the wireless medium, especially when handling small data frames. Wi-Fi 6 introduced OFDMA, which is a different modulation, which allows the access point to use frames to multiple clients in one transmission. As you can see in the image, the channel is fully used to carry data to multiple clients without any wasted spectrum. And it achieves this by subdividing the channel into smaller subcarriers and group them into resource units, or usually referred to as RUs. These resource units are assigned to different clients, which allows the access point to serve them simultaneously during uplink and downlink transmissions. And the number of RUs or resource units assigned to each user depends on the traffic type and the bandwidth capabilities of the client. So OFDMA optimizes the wireless medium usage to serve multiple clients, which is highly desired in dense wireless environments. To further explain how OFDMA works, we could use the analogy of a delivery truck. While OFDM uses a truck per single delivery, which is not efficient with small packages, OFDMA uses the same truck to deliver multiple packages to multiple destinations on a single trip. So the main benefit of OFDMA is that it uses the wireless medium more efficiently in the sense that there is no wasted spectrum when transmitting data. Another feature that was introduced in Wi-Fi 6 is called BSS Coloring, which is designed to reduce contention over the wireless medium, specifically in a dense environment with multiple access points operating in proximity. Before we dive into explaining what BSS Coloring is and how it works, let's first define what a BSS is. A BSS, or basic service set, is made of an access point and one or more wireless clients. In this example, we have 4 basic service sets, and the access points are deployed close enough to hear each other. A major problem that can happen in such a dense wireless environment is overlapping BSS, which describes a situation where 2 access points are operating in the same channel. In this example, we have access points A and B operating in the same channel, which is channel 6. Now let's focus on these 2 access points to understand what happens when there is overlapping BSS. As you might know, wireless devices use a mechanism called CSMA-CA to sense when the wireless medium is busy or available for transmission. And this mechanism is used to avoid collision among stations transmitting over the same channel. With overlapping BSS here, access point B is picking up the frames sent by computer A even if it belongs to a different BSS, which causes the access point B and computer B to put off their data transmission. This happens because the wireless standards prior to Wi-Fi 6 did not include any identifier of the BSS in the data transmission. And this brings us to BSS Coloring that was introduced in Wi-Fi 6. It basically defines a new value in the PHY header that defines intra-BSS transmission to allow the access point and wireless devices to determine frames belonging to a different BSS. So with BSS Coloring, wireless devices can ignore transmission from an overlapping BSS and therefore can transmit at the same time, which eventually reduce the chance of multiple devices interfering with one another even if they belong to different BSS. In this example, we use channels from 2.4 band But the same thing can happen when using multiple APs in proximity in 5 GHz band. So the main reason of adding BSS coloring in Wi-Fi 6 is to reduce airtime consumption and avoid interference that is the result of overlapping BSS, which is usually referred to as co-channel interference. So far we've seen how multi-user MIMO technology, OFDMA, and BSS coloring improve the wireless performance in a high-density environment. In addition, Wi-Fi 6 introduced 1024 QAM, which is a highly developed modulation scheme designed to increase the data rate between access point and wireless client. So while 256 QAM modulation 802.11ac carries 8 bits per symbol, 1024 QAM in Wi-Fi 6 carries 10 bits of data per symbol, which increases data rate by 25%, and it achieves this by including more data in each transmission. In a nutshell, higher QAM levels increase the data rates by constructing signals that carry more bits per second. Wi-Fi 6 also introduced longer God interval options to protect against signal delay. God interval is a feature that you have probably seen in the access point configuration. Let's briefly explain what it is and what it does. A God interval is a period of time between symbol transmission. In 802.11ac, the access point will transmit a symbol and pause for 0.8 microsecond to allow the client to receive and process the symbol before sending a new symbol. The reason we need God interval because of propagation delays. Knowing that symbols take different paths to reach a destination, and since they do not all arrive at the desired time, God interval is an idle time used to protect against inter-symbol interference when there is propagation delay. So 802.11ac supports two options for God interval, 0.4 and 0.8 microsecond. And you've probably heard that choosing the short God interval, 0.4, will increase your data rate by approximately 10%. This happens because a short God interval reduces the idle time between symbol transmission. Wi-Fi 6 now offers 3 God interval options, 0.8, 1.6, and 3.2 microsecond. Not only that, but it also increased symbol duration 4 times as shown in the slide. Longer symbol durations can be very helpful in outdoor deployments where the delay spread is usually larger than indoor places. Just keep in mind that a longer GI protects against inter-symbol interference and lowers the data rate, while a short GI increases data rate but also increases the chance of getting inter-symbol interference. To reduce power consumption and medium contention, Wi-Fi 6 introduced target wake time feature. The main goal of target wake time is to save power on the wireless devices by enabling them to determine how frequently they will wake up to transmit and receive data. In addition to conserving the battery life of wireless devices, target wake time enables the access point to determine the schedule of when the wireless devices can access the wireless medium. And this helps reduce the contention over the medium and improve the spectral efficiency. As we have learned in this tutorial, Wi-Fi 6 has introduced important features mainly focused on improving the Wi-Fi experience in high-density environments and increasing the wireless throughput of wireless clients. Just remember, to take full advantage of these benefits offered by Wi-Fi 6, the access point and the wireless client both need to support and use Wi-Fi 6. These are just some of the main features, that make it worth considering Wi-Fi 6 capable access point in future deployments. Thank you very much for watching. I hope you enjoyed this video. Leave us a comment below if you have a request for any future videos. And don't forget to subscribe to our YouTube channel to keep up to date with all our videos. Have a great day, and I'll see you in the next video.